How the jet engine industry generates $160 billion, the global economy moves on wings. But those wings are useless without the concentrated power of the jet engine. While passengers marvel at the comfort of modern cabins or the speed of international travel, the true miracle of modern aviation remains hidden beneath the wings. The jet engine industry is not merely a manufacturing sector. It is the invisible power that sustains the flow of global trade, tourism, and diplomacy. Without these machines, the concept of a global village would collapse, reverting the world to a state where crossing oceans took weeks rather than hours. A modern turbofan engine is arguably the most complex and expensive machine ever mass-produced by humanity. A single unit for a wide-body aircraft such as the General Electric GE9X can cost upwards of $45 million. This price tag reflects not just the physical materials, but the decades of extreme engineering required to ensure that a machine can operate at temperatures higher than the melting point of its own components, while spinning at thousands of revolutions per minute for 15 hours straight. Without a single second of failure, the architecture of a high-bypass turbofan is a masterpiece of precision. Each engine consists of approximately 30,000 unique components, each manufactured to tolerances measured in microns. Developing a new engine architecture is a financial gamble of epic proportions, often requiring an initial investment exceeding $1 billion in research and development R&D. This high barrier to entry ensures that only a handful of companies on the planet possess the technical and financial know-how to compete in this elite tier of heavy industry. The scale of the market is staggering. Annually, the industry produces roughly 3,000 large commercial engines to meet the demands of airframe manufacturers like Boeing and Airbus, when factoring in original equipment manufacturer OEM sales, long-term service agreements, and the secondary parts market. The industry generates a total annual revenue of $160 billion. This figure is expected to grow as the global middle class expands and the demand for narrow-body aircraft in emerging markets reaches unprecedented levels. The landscape is dominated by a small group of invisible giants. General Electric, GE Aerospace, Rolls-Royce, and Pratt & Whitney form the primary triumvirate, often working in joint ventures such as CFM International with Safran Aircraft Engines, or the International Aero Engines IAE Consortium. These companies do not just sell engines, they sell power by the hour, a business model where the airline pays for the time the engine is operational. Shifting the focus from a one-time sale to a 30-year relationship of maintenance and monitoring, the economic impact of the jet engine industry extends far beyond the assembly lines in Ohio, Derby, or Connecticut. It supports a golden chain of thousands of Tier 1, 2, and 3 suppliers, from specialized forging houses in Italy to software developers in India and precision sensor manufacturers in Japan. The supply chain is a global web. A single delay in the production of a high-pressure turbine blade can halt a multi-billion-dollar production line. Demonstrating how deeply integrated this industry is with the global GDP. The criticality of the engine industry was never more apparent than during recent supply chain disruptions. When the flow of spare parts slows down, aircraft are grounded, logistics networks fail, and the cost of consumer goods rises. The maintenance, repair, and overhaul MRO sector is a $90 billion sub-industry that ensures the world keeps moving. The reliability of these engines is so high that we often take for granted the logistical precision required to keep 25,000 aircraft in the sky simultaneously. To achieve modern efficiency standards, engineers have turned to exotic materials, single-crystal superalloys, capable of withstanding centrifugal forces equivalent to the weight of a freight train. More recently, ceramic matrix composite CMCs have revolutionized the industry. These materials are lighter than metal and can operate at temperatures where traditional alloys would turn to liquid. The cost of developing and sourcing these materials is a primary driver of the $30 million, $2 $50 million price point for modern power plants. The industry is currently facing its greatest challenge: decarbonization, the transition to sustainable aviation fuel SAF. Hybrid electric propulsion and hydrogen combustion is no longer a theoretical exercise. Companies are investing billions to ensure that the next generation of engines reduces 150%. This technological pivot represents the largest capital reallocation in the history of aerospace, as the industry seeks to maintain its $160 billion valuation while achieving net zero targets by 2050. Jet engine technology is a matter of national security and strategic autonomy. Only 5 nations, the United States, the United Kingdom, France, Russia, and recently China, have demonstrated the capability to build high-performance jet engines from scratch. This engine gap is a major geopolitical lever. The ability to produce indigenous engines determines a nation's ability to project power and protect its commercial interests without relying on foreign intellectual property. The innovations born in the jet engine lab often find their way into other sectors. The high-efficiency turbines used in natural gas power plants are direct descendants of jet engine technology. The additive manufacturing 3D printing techniques pioneered to create complex cooling passages in turbine blades are now used in medical implants and high-performance automotive parts. Thus, the $160 billion industry acts as a catalyst for broader industrial advancement across the globe. In conclusion, the jet engine industry is the backbone of modern civilization. It is an empire built on the mastery of thermodynamics, materials science, and global logistics. As we look toward 2030 and beyond, the industry will continue to be the primary driver of economic connectivity. Whether through the roar of a takeoff or the silent efficiency of a high-altitude cruise, the $160 billion generated by these machines is the heartbeat of a world that refuses to stand still. The next frontier in propulsion efficiency is the open fan architecture, most notably championed by the CFM-RISE, Revolutionary Innovation for Sustainable Engines program. By removing the traditional engine nacelle, engineers can achieve ultra-high bypass ratios that were previously physically impossible. This silent revolution aims to reduce fuel consumption and CO2 emissions by more than 20% compared to today's most efficient engines. The strategic value of open fan technology lies in its ability to bridge the gap between current liquid fuel reliance and the radical airframe designs of the future. The industry is undergoing a massive digital transformation through the implementation of digital twins. Every physical engine in service now has a virtual counterpart that mirrors its performance in real time using data from thousands of IoT sensors. This allows manufacturers to move from reactive repairs to predictive maintenance, identifying potential component fatigue before it occurs. By optimizing the on-wing time of an engine, digital twins maximize the return on investment for airlines and significantly reduce the multi-billion-dollar costs associated with unscheduled groundings. While the sale of a new engine is a high-profile event, the true economic engine of the industry is the MRO maintenance, repair, and overhaul sector, representing a $90 billion annual market. MRO ensures the longevity of assets that are expected to fly for 25 to 30 years. Strategic control over the MRO lifecycle allows OEMs to maintain high standards of safety and reliability while securing a steady stream of high-margin revenue. In an era of supply chain volatility, a robust MRO infrastructure is the difference between a functional global fleet and a logistical standstill. Additive manufacturing, or 3D printing, has moved from prototyping to the heart of jet engine production. This technology allows for part consolidation, where hundreds of individual components are merged into a single, complex printed structure. For example, fuel nozzles that once required 20 separate parts are now printed as one, resulting in a 25% weight reduction and significantly improved durability. This shift not only enhances engine performance, but also streamlines the global supply chain by allowing parts to be printed. Closer to the point of need, the industry's commitment to net zero by 2050 is driving a dual-track energy strategy. In the short term, Sustainable Aviation Fuel SAF provides a drop-in solution that can be used in existing engines to reduce life cycle carbon emissions by up to 80%. In the long term, the industry is exploring hydrogen combustion and fuel cell technology. Transitioning to hydrogen requires a complete redesign of the engine's fuel system and the aircraft's storage tanks, representing the most significant engineering challenge since the dawn of the jet age. This path is not just an environmental necessity but a strategic imperative to ensure the industry's social license to operate in a decarbonizing world.